It would be easier if we had like real numbers, because then I could have done it on my own, but I was like having to make sure I had the same like fake numbers as y'all did.
0.2 and 2.1. Wait. Yeah.
Where's the last decrease?
Use estimation to identify the intervals where the graph
Oh,
is
there's
decreasing.
another one?
Yeah, I was gonna say, you
So let's just circle.
I can just tell you.
Yeah, what is it? That's what I did.
2.9.
Yeah, we got the all.
Yes.
How many should there be?
Okay. Really quickly, I didn't even check anyone's book or answers on this. What did y'all say about the a value of this function?
Negative.
Negative. Why do we know it's negative? It's flipped. Okay. Remember, it's definitely not a parabola. It's not a quadratic. But if it was a quadratic, it'd be concave down. Do we see how that is telling us, right, that it is a negative a? And the in behavior tells us that as well. And so the fact that it is most similar to a parabola tells us, is it even or odd? Notice, remember, a parabola is x to the second. So when it has in behavior similar to a parabola, it's an even degree function. We good on that idea? Any questions? KJ, you sure you're good? Okay. Jane, you good? Alright. So can this function be a 6th degree polynomial? So this is actually going to be a really important discussion point. What did y'all think? I only heard one group's discussion on this. You said yes? You skipped it?
I said yes.
You said yes?
I thought it
Yeah, we
was
said yes.
counting the amount of times like up, down. But I'll probably like.
So how many times does it go up?
3.
3. How many times does it go down?
3.
So there's no guarantee that that's always going to be the case, but it is interesting that there are 6 intervals, right? So how many, so what would the possible degree be? 6. But how many x-intercepts did we have?
4.
Only 4.
Well, there could be like double, right, or imaginary.
Actually look at it. Are there any double? Could there be any double? No, why not? Remember, if it's double, it's going to touch and then go right back away.
Doesn't that just mean it's like negative though if it doesn't cross the x-axis, like if it just stays down here and keeps going, like?
Well, it's more that you see how here it doesn't touch the x-axis, but it goes down, up, and back down. That means that there's imaginary roots somewhere in there. Does anyone know how imaginary roots work? Like how many times, if you have one imaginary root, is that possible?
You're making it sound like it's not.
That's a great question, is it? So remember, the only way to get an imaginary root is to do what? Take the square root of a negative. If I take a square root of a negative, what do I automatically get? Yes and I, but there's something else. I'm missing something here.
Irrational.
1.
I took a square root. So if I take a square root to get an imaginary root, it's always got to be how many? 2. I agree with you. I need y'all to pay attention to this because this is an important idea. If I take a square root to get an imaginary root, I always have a plus or a minus, so imaginary roots always come in pairs. They always come as a duo. Imaginary roots always come as a duo. And so that is an important detail to notice. So if there is an imaginary root here, there's actually how many? 2. So 1, 2, 3, 4, 5, 6. So could it be a 6th degree? Yes. So, and again, I'm going to use the language at least 6 roots. For real roots, again, I know they're real because they're intersecting the x-axis. Those are real roots. For real roots and 2 complex are guaranteed.
So, the zeros are when you touch the x, right?
Not quite. An x-intercept is where you touch the x-axis. Is where you intersect the x-axis. A 0 just means that the y value is 0. Notice, so if I had x squared plus 4, that's a parabola. That parabola would look like this. Does that ever touch the x-axis? No. So I don't have any x-intercepts. But notice how the y value right now is 0? So I can still have,
I used to have zeros.
you can have imaginary zeros. You cannot have imaginary x-intercepts. A 0 is almost synonymous with root. Like they're on, I don't think there's a real difference, at least I haven't been able to find one. An x-intercept though is only a real 0. Okay? So I'm still having imaginary roots there. One other thing that I do want to share with you, and I want you to notice this, go look at number 12 really quickly. How many relative extrema did you have on number 12? 4 relative extrema on number 12, right? But what did we say the power was? Or the degree, sorry.
Wait, on number 12. Which one on number 12?
There's only one number 12.
Yeah, but
That's
that's
page
page
12 right now.
But there's only one problem that talks about relative extrema.
Yeah.
The one that says relative extreme.
So how many relative extrema? 4. What did we identify the degree as probably being? Didn't we say 5? Right? Because we're asked if it could be a cubic function. We said no, it can't be cubic. It could be quintic. Thanks, sir. Alright. So I want you to notice here with the 6th degree polynomial. So now we have a degree of 6. And how many relative extrema do we have? What do you think the connection is between the relative extrema and the degree? One less. Now, it's not guaranteed to be 1 less, but you can have up to 1 less, and that's one of the difficult parts. But the relative extrema, the fact that I have 5, gives me a strong indication that the degree is probably 6.
Why is it 1 less? Is that what it always be?
No, it will not always be, it always can be, which is a weird way to put it, and it ties into a concept in calculus known as a derivative that y'all just haven't studied yet. But the reason why I say it could be up to 1 less, notice here's y equals x cubed. Are there any relative extrema in this case? No. But it could, a cubic could look like this. Now, how many relative extrema do we have? 2. So it can be up to 1 less than the power, or the degree. So it's not guaranteed to be 1 less than the degree, but it can be up to 1 less than the degree. Okay? Negative infinity to 2.2. I think up to this point, we were all the same. So 3 relative max, 2 relative min, 1 absolute max. We all get through there? Is that what we said? I want you to notice, what is the most we've ever had with an absolute max or minimum? How many absolute max or min? Remember, infinity is not a number, so we can't actually quite get there. How many absolute extrema do we have on the previous problem? 0. Here we have 1.
You only have 1?
1 is the most for the absolute. Because remember, if it's a cubic or an odd degree, can you ever have an absolute for an odd degree?
You could have a, what you mean, like a max?
Can you have an absolute max or min when it's odd?
No, there's gonna be infinity.
It's going down to negative infinity, going up to infinity. So if it's odd degree, yeah, you have no absolute.
But if it's absolute, you have 1 of each, right?
If it's even, you mean?
Huh?
If it's an even degree?
What you saying, if it's an absolute, like max or min?
The most number you could have is 1. Notice it's either an absolute minimum or it's an absolute maximum, because if it's an even degree, it's either going to continue up for forever, so you can't have an absolute maximum, or it's going to continue down forever, so you can't have an absolute maximum. Right? The end behavior prevents you from having more than one absolute extrema. Okay? Does anybody want me to go over the intervals of increasing and decreasing? I think I saw all the same for everybody. Okay. So, what we want to move into is activity 3.3 now. The zeros of polynomial functions. So this is going to help us understand the relationship between zeros and extrema a little bit better, and the degree. So notice it's trying to analyze the tables, describe any similarities or differences you notice. I want you to notice here in the linear and in the quadratic, when it's talking about the zeros, it says that there's one real zero. And here there's two real distinct zeros. So what do we mean by real zeros? How do we know that they're real? So what would we call those zeros, or those roots? We could call them x-intercepts, couldn't we? So we have real zeros when the words x-intercepts. So real zeros equal x-intercepts. Okay? Real zeros equal to x-intercepts. Real zeros equal to x-intercepts. So why in the world here do we know that it's two imaginary zeros? So we know it doesn't have any real zeros. How in the world does the person who made this textbook know there's two imaginary though? No? Okay. It doesn't touch the x-axis, which tells us that there's not real zeros. So why does it have two imaginary? I'm going to make up a possible equation here. Maybe that's the equation for this parabola. Maybe, because I don't have any numbers. Why do I know that there has to be two imaginary? Because they do come in pairs. 2, it's x squared, right? And remember, the number of zeros matches the degree. So are there any real zeros here? No. But aren't there two zeros no matter what? It's a second degree, so it has to be two zeros. So if they're not real, they have to be imaginary. It has to be imaginary. If it's not real, it has to be imaginary. And then we look over here at a cubic. How many zeros does a cubic have to have? 3. Look at every option. How many zeros are there? Right? Sometimes it's a multiplicity of 3. Right? Sometimes we have a multiplicity of 2 and 1. Sometimes we have a real and 2 imaginary. So we need to notice this pattern of how these zeros are happening, and notice in some cases, right, when I look here at the cubic function, how many extrema did I have? 2, 1 less than the degree. Here I had 2, here I had 2. Notice there are some cases where we don't have the 2 though. So we wanted to see how those things are working. To understand this a little bit more, I do want you to work within your small groups on this quartic function, which is on the next side. Work within your small groups to figure out how many zeros there would be, and try to do a sketch similar to what we have over here. Paying attention to the fact, if it's quartic, how many roots does there have to be? 4. If it is a quartic, it has to be 4 roots. So keep that in mind, paying attention to those different ideas. Let's work with our small groups to come up with possible graphs and number of roots for each of these. Alright? Let's get to work.